So far we've concentrated on volumetric contributions to Gibbs free energy, really. So we've written that molar Gibbs free energy is a combination of chemical potentials. In other words, we're just concerned with the mole fraction of A times that chemical potential, remembering, of course, that chemical potential is a function of composition as well as external conditions like pressure and temperature, and then a similar term for component B. But there's also energy and entropy associated with the boundaries between phases, for example, that is proportional to area. And so there's an additional term that we might wish to add here, which is this, essentially an excess free energy, where this coefficient gamma contains an energy contribution. Yeah?
What's going on? Like a title or something?
So this additional contribution from interfacial area, it can arise from energy. So you can imagine that you've got slightly different bonding configurations that go on at the interface. There may be a contribution, so if we call that one energy, and these are all obviously per unit area here. There could be an entropy, contribution there. And also there could be pressure, and so you could have some volume. So you might imagine that the presence of interfaces in your material might actually change the volume actually you have. Maybe it is because the interface structure is more open than the normal bulk. This last one would be associated with essentially with a change in density, and so typically we neglect that one here. Okay, we'll not worry too much about that one. More importantly is this energy per unit area and the entropy per unit area. Okay, so when we've got, for example, phase separation, we've got components, we've got regions of alpha phase and beta phase, then we're interested in what the excess free energy is for the interface between those two phases due to energy and entropy. So what you can see here is that gamma is the work to create a unit area of interface in a system. Okay, that makes sense. That's or create a unit area or an area A in my sample, and the Gibbs free energy will increase by gamma times A. So gamma is this work done. You're probably familiar with surface tension when it comes to interfaces in liquids. Surface tension is to do with work done to stretch an area of interface. Let me write this down. We've got G up here is proportional to gamma times A, the contribution that depends upon the area. And so dG, we could write, is gamma dA plus A d gamma. Just taking the total derivative of gamma times A. And force, if you like, is sometimes associated with a line tension or the force that I need to apply. So in other words, if you imagine I've got some area of interface here, there's excess energy associated with that. So you would like to minimize the area there, which means that essentially, if you imagine that this area is being maintained between two parallel lines, essentially I have to apply a force F on the right here simply to maintain this area, because actually normally it would otherwise want to shrink back if it could. So that means you write force like that, and if you compare those two lines, it's therefore true that the force can be written like that. Okay? Now just think about this term here. This is the rate of change of the coefficient here, the excess free energy per unit area, how that changes with area. Now, if you have a liquid, then when you create extra surface area of interface, the structure doesn't change because the liquid can move around and reorganize itself all the time. So for a liquid, this term is 0. And therefore you get the result that you may be familiar with, that in a liquid, surface tension, the energy per unit area, is also equal to the line tension, the force to maintain the area. Okay? But that is not true when it comes to solids. Okay? So it's just worth, this line here is just to, let me just write, so this derivative vanishes for a liquid. Okay, make a note of that there. It's just to say that if you've seen this before, you've probably seen it in the context of surface tension, and there's a slightly sort of special case there. In solids we have an additional term as well. Okay, this one here. So the interfaces that we want to discuss might be of the following sort. So first of all, the interface between crystal and vapour. So you've just got a gas above a solid surface. Then crystal with a liquid. And then internal interfaces, i.e. you've just got solid and you've got an interface between two different solids inside here. And the point is that these are, they're in order of increasing complexity. Okay? By which I mean, if I've got a crystal vapor interface, then what do I care about? Well, all I really care about is, if I imagine the crystal sort of defining my system of axes, my reference frame, then all I really care about is what is the orientation of the interface, assuming it's planar, between solid and vapor. And so the orientation of a plane has 2 degrees of freedom. So that's all there is for this first example. That's pretty straightforward. The crystal liquid one is slightly more complicated because the liquid might be structured in the vicinity of the interface. So there are certain things that are known about the behaviour of liquids near solids, double layers and things like this that you can get in them, a structure which makes them more complicated than a crystal with a vapour. You might just think liquid and liquid and gas, what's the difference between them? The difference is in this potential of ordering in the liquid phase. And finally, with the internal interface, any idea how many degrees of freedom there are there? Between two solids. So it's grain boundary.
And it's monophasic?
Sorry, what's that?
Is it monophasic?
Okay, yeah, let's assume it's the same crystal structure. Yeah.
And here the orientation happens.
Yeah, for both entities plus the boundary, so 8.
Okay, not quite as bad as 8. But I think you're counting the number correctly.
You mean should we use each phase?
So you've got what I said with the crystal vapor one was that you could take one crystal as kind of just set because it's only relative orientation that matters.
Right, so 5.
So 5. Because if I take one, all that really matters is the orientation of the second one compared to the original one, the relative orientation of the two. So with the second one, I can obviously there are 3, right? Because I can take a direction in the first crystal and tell you what I need to do to rotate that into the equivalent direction in the second crystal. So that's 2 degrees of freedom. And then I can rotate it around that axis. Does that make sense? So that's that. There are 3 degrees of freedom essentially defining the relative orientation of 2 crystals. So over here I know I've got this crystal, over here I've got this crystal, but I've said nothing so far about the orientation of the interface between the 2. It could be like that, or it could be like that, or it could be like that. So there's a planar orientation there that requires another 2 degrees of freedom. So I end up with 5. So there are 5 degrees of freedom there. Okay, when it turns out to when we're talking about grain boundaries. So that just sort of shows you how it becomes how these things are more complicated. Okay, if you want to discuss these things. Now, when does this stuff? When does it matter? When do we worry about? When do we worry about interfacial area? Evolution of the microstructure with time. At what stage? At what stage is the interfacial contribution?
After the rate transformation has occurred, time is just passing and rate growth.
Okay. Yeah. Anyone else got any thoughts on it? Yeah, true. Why could we get away with it? I mean, up till now we've ignored that pretty much. Why do you think we could do that? Why in general? So when you do. You've done it in electronic structure as well, haven't you? You have no interfaces there.
Is it because the size of the ball CG is so much larger than
The size of the...
The size of the ball is so much larger than
Right, okay, yes. Because the terms that depend upon the volume there dominate massively compared to any terms that are defined by the surface. But you've done in electronic structure of materials, what were the boundary conditions that you used there? Periodic. Where are the surfaces? There aren't any. Did that matter? No. Were you given a justification for why that was okay? You're describing this as you're coming up with an electronic structure of electrons in a crystal, only this crystal has no surfaces, unlike any other crystal web actually that exists in real life. Yeah? And it's because the surfaces just make a contribution which is proportional to 1 over the number of atoms, let's say. 1 over the number of atoms to the 2/3 or something like that. As n gets very large, that contribution just gets very, very small. So it will only matter when we have an awful lot of surface area in our system, when the interface is, when there's a lot of interface per unit volume, and that is when things are at a very small stage, when you've got lots of little sort of things emerging from the soup. And this just goes back to nucleation theory. Let's consider this then. Let's consider that I've got a parent phase alpha, and then okay, so I've got an alpha phase, like this, and I want to carve out a cavity in alpha and replace it with beta, in order to kind of think about the nucleation of a beta phase within an alpha phase. Okay? So we could write that the Gibbs free energy change for this is the number of atoms in the cluster times the difference in the chemical potentials for the two phases, and then you've got so these are assumed to be bulk chemical potentials. Gamma, I am making a simplification with gamma. Gamma I previously talked about before as an energy per unit area for a flat interface. So clearly here I've got a spherical interface, so I might need to worry about that a little bit, but bear with me there. Okay, in other words, what I'm trying to model here is competition. We're going to assume that, we better assume that we need to have mu beta less than mu alpha, okay, in order to want to do this. So the bulk, the chemical potential in the bulk for the beta phase is less than for the alpha phase. Okay, so we want to drive this. There's a driving force here because this term in brackets is negative. So the more atoms you lock up in the beta phase, then the lower the energy you're going to get. But also, as you lock more atoms up in the beta phase, so you're increasing the area of interface between the two, and that costs you gamma per unit area. Okay, so N, of course, is just the volume of the cluster divided by omega, which omega, I think I might have used this before. Omega is the volume per atom, which I'm assuming is kind of the, I suppose strictly speaking it's the volume per unit atom in the beta phase, but let's assume that those are pretty much the same between two phases. Okay, so my delta G is 4 pi over 3 omega times r cubed times the difference in chemical potentials So the point is that there is a quite a flat negative term that goes cubic in R. Okay, proportional to R cubed, that is from the bulk term, and then proportional to R squared is the surface term. One is negative, one is positive. So put them together, and as ever, I've drawn this badly. Okay, it will do something like this. Okay, it's not going to quite do that at that point. But clearly the R squared term always wins when R is small, and then at some point when R gets bigger to some limit, R star. Sorry, that's not R star there. That's just at some point the energy to the excess. Well, so the energy to expand the nucleus of beta stops increasing and starts decreasing. So inevitably we just take the derivative. Okay, and if we set that equal to 0, that tells me that there's a critical radius, which is 2 times omega times gamma. Sorry, I'm just going to turn the I've turned the difference between the two chemicals potentials around here. Here it was mu beta minus mu alpha. Here I put mu alpha minus mu beta because of my assumption over here. So everything in this expression here is positive, so that the radius is a positive number. Okay. And if I put in if I look at if I substitute now R equals R star in my expression for delta G and do all the algebra, then I get that expression. Okay, that's just algebra. I'm sure you're perfectly capable of going and checking that out. Yeah.
Why is mu alpha larger than
Sorry, why is
mu alpha larger than mu beta?
because as what I said is if that's what's the driving force we want to do. We're assuming that we're under conditions of pressure and temperature here, where the formation of beta is something that we would like to happen thermodynamically. So beta is more stable than alpha, but I have alpha and I want it to transform to beta, and so that's therefore, if that weren't the case, then in fact the this term here would also be positive, and so the Gibbs free energy change would always be increasing, and there would never be any driving force. Here I've got a bulk driving force that wants the beta phase to grow, but I have an interfacial area term that is costing me energy. Okay? And so what you see is that there is a critical radius that this spherical beta phase needs to reach before it becomes energetically favourable for it to grow. Okay, before the Gibbs free energy starts to decrease as I try to increase the radius, rather than increasing as I try to increase the radius. And this is just a classical model of nucleation, right? This is, remember, right back at the beginning we discussed the difference between spinodal decomposition and nucleation, and I explained that nucleation was an activated process, and there was some energy barrier that you had to get over. Well, here is the energy barrier, right? The energy barrier, delta G star, is the energy barrier that you would have here. And that's where it comes from. So in other words, it is the interfacial area thing that actually is really responsible for the barrier for nucleation, the cost of creating that interface between the two phases. You remember? Sorry. Let's get going.
I just want to ask, why is it not the crossover point where the changes here that's more significant?
You mean this one?
Yeah, because
that's the point at which you've gone back to. That's the point at which you could create.
Is that the curvature? Because the curvature of G star is negative at that point, or it's always negative throughout. What I'm saying is
going to answer your own question.
What?
I'm saying you're going to answer your own question.
I've answered it.
Are you sure? I'm not sure you quite have. I'm not sure you have.
But I'm saying,
I'm not sure
why is that not significant?
The crossover point. Well, the crossover point is different. The crossover point is the radius of a nucleus that I could create at zero energy cost. So I could carve out that larger radius and replace beta with alpha, and it would cost me nothing to do it. Okay. The problem is, in real life, I cannot do this thought experiment where I just carve out the spherical cavity of a piece of material and replace it with something else. The only way I can do things in practice is to add individual atoms onto an existing nucleus or take them away. Okay? And when I'm doing that, what I can see is that below here, at this point, if I take atoms away, I lower the Gibbs free energy. So that's favourable. There's a driving force, and the driving force here would actually be wanting to make that nucleus shrink. Whereas if I'm over here, then the driving force wants to make the nucleus grow, because that will reduce the Gibbs free energy. Remember, a system has a Gibbs free energy, right? In a particular state, it has a Gibbs free energy, and what it wants to do is to minimise its Gibbs free energy. It doesn't know about what might be happening way over there. All it knows is if I go in this direction, I decrease my energy, and if I go in that direction, I increase my energy.
Yeah, it's because I was thinking delta.
Yeah.
I thought I've seen a delta there on the change, as I did when we were doing gradually before. So
yeah, sorry. Maybe the delta is not particularly.
It's still always an increase.
It is still in. Yeah. No, the delta is not. It's not. Yeah, no. There's nothing. I'm not trying to do anything to cover the second derivative here. Just asking that question. Yeah. Sorry, your question. Or was it the same as this question?
Yes, essentially, if the process is happening without nucleation, okay, it's convenient, then would you still have any interfacial cost of energy due to interfaces that occur?
In the spinodal?
Yeah.
Is that what you're talking about?
Yeah.
Yes, I see what you mean. Yes. Yes, they kind of, well, they, in the, okay, so in the model where we derived the spinodal, we didn't really have interfaces, right? We always had a random ordering of A and B atoms. And so there was no concept of an interface. So in fact, okay, so you're right that in that case there was no sense in which the nucleation did not arise from an interface explicitly there, whereas the reality is that actually, in practice, that's an extra term which also gives you. So in other words, with the nucleation picture in that quasi-chemical approach, there was an energy barrier even before you considered the interfaces, which we didn't talk about there. Yeah, there already was some sort of barrier. Whereas in the spinodal, what we looked at was, and there we did look at the second derivative, and we looked at what wanted spontaneously to happen, and we saw that just the infinitesimal kind of change was still energetically favourable. And under those circumstances, the idea of the interface is not quite as, it's not quite so clear what it means. If I have a sample of material and a little bit changes composition slightly more rich and the other changes composition slightly less rich, that's what we were talking about, then in what sense is it meaningful to try and divide very precisely between them with an interface? Essentially there kind of is no interface because the difference between the two phases is infinitesimal. So actually, essentially under those circumstances, gamma is naught. It's not that there won't, it's not that as things evolve and finite changes occur, that you won't end up with interface. You very clearly do it when you look at the micrographs of things that have gone through detectex, and you see very clearly, don't you, the stripes and the interfaces between them. So there are interfaces there, and they will cost energy. But at the point at which you first began that process of separation, there was no energy cost to do that. It was energetically favourable to do that. Whereas when we had to do so that was for the spinodal. In that picture, when we had to do the nucleation outside the spinodal, you actually still had to go a finite. You couldn't do it. Nothing was energetically favourable until you made a finite separation into two compositions. At which point there is an interface between them. Does that make sense? So the difference between whether it's energetically favourable or not to make the infinitesimal separation between the two. Because if it's energetically favourable to make an infinitesimal separation between the two, that's inside the spinodal, then there is no interfacial energy cost for the infinitesimal separation. So the spinodal still occurs and it still proceeds, and it's energetically favourable in the way it's spontaneous, but you will end up with interface. Whereas outside the spinodal, the infinitesimal separation is not favourable, so it doesn't happen. So you can only make it happen actually by nucleation, by a random process of assembling something a bit like this, and part of the energy cost of associated, because as soon as you create something which is kind of finite, it then has the interface, and you then have to count its energy, and therefore part of the a major part of the nucleation energy cost is then that area thing. So when we did the thing with nucleation versus spinodal, we couldn't say what I couldn't tell you what the energy barrier for nucleation was from that level. This is a way of how to tell you what it was. Does that make sense, people? I appreciate that's a good point. Could you explain the answer to your question to someone else now?
In the model that we considered before, I think it's the infinitesimal level. There is no place where interface can be treated. Like it just doesn't come into but there is still I don't remember off the top of my head what the energy barrier was in that group, but there's still an energy barrier which we were not able to evaluate that is treated.
Good. Okay. The energy barrier, if you remember, was about the chord between 2 points on the curve and whether the chord lay above the free energy curve or below the free energy curve, which depended upon the curvature, whether it's concave up or concave down.
Okay.
Yeah, it was to do about the energy of the two phases with slightly different compositions compared with the fully mixed, and whether the separation had energy higher or lower. Yeah, it had nothing. It had no area of interface in between. Good. You have a question?
Yes. So
No, sorry, it's delta G because it's just a change. It's just a change in energy of that picture compared with a picture that is just pure alpha everywhere. That's why I called it delta G. Sorry. Yeah.
So after assuming that we can overcome the energy bound, the height at which we can lower the energy, right? This is the radius. Does nucleation just happen to grow larger?
So nucleation. Okay, what you now have to imagine is, okay, we can now imagine our atoms in all sorts of random motion, diffusing around, knocking about. Okay, there is a probability that the atoms will knock about such that a certain number of them find themselves in a beta phase configuration in a particular area of space. Okay, that's just what happens with fluctuations. Okay, so suppose there's a fluctuation that happens here, and it will tend to shrink back. If there's a fluctuation it just manages to get there, then it will grow. So the point is that actually the chances of it happening are very, very small, but you've got Avogadro's number of them around, so it will happen sometimes. And that the ones that get over this will then spontaneously increase in size. They will then grow. Okay? And in fact, have you done Ostwald ripening? We discussed that. The larger ones will always grow at the expense of the smaller ones. Okay? Because as the larger you get, the smaller the ratio of surface area to volume. It's the volume energy that is driving this, and it's the surface energy that's costing you this. So you have a system in which you just have one big nucleus and one small nucleus. Even if they're both above the critical size, eventually the average energy of an atom in the small one is higher than the big one because its surface area per atom energy is higher. So actually it will want to diffuse to the big one. So the smaller ones will shrink, disappear, and the big ones will grow. But that's different from nucleation. Okay? Nucleation is all about the fact that you have to get an assembly of atoms together past this point, and then it will grow. Okay? That makes sense? Okay. All right. Good. Any more questions? Yeah.
No, it's fine.
No? The questions are valuable. Remember, the questions are valuable. Okay? It really doesn't matter if we don't cover any more material in this course. If you're getting a deeper understanding of what we have covered, and particularly being able to start to relate different bits, that is kind of the aim. That you can see it coherently, and it's where the pieces of the puzzle don't quite fit together that are probably actually significant. So it's fine to ask.
Okay. So if you're saying that the larger nuclei will always grow in expense of the smaller.
Sorry, I shouldn't have used the word nuclei probably, but the larger regions grow. Yeah, go on.
How do you end up with grains? So are they all around the same scale? Sorry. This is a really
so sometimes I don't. So sometimes I do. So sometimes I don't. So there's a process called coarse. Sometimes it's called coarsening, and it happens. But of course, in order to happen, you have to have long-range diffusion occurring. So you have to be at a temperature.
Okay.
So, for example, if you okay. So one of the. Do you remember the picture I showed of the equiax aluminium alloy? Which was in the very first lecture I showed some micrographs, and I showed one where they all look nice the same size, didn't I? And then I pointed out the dots, the black dots in the middle, because they were the titanium diboride nucleating agent. So now you know.
Yeah.
Okay, because the point was, generally speaking, the lecture itself, nucleation creates a mess. Yeah? And it's not evenly distributed or anything like that, so you have to help it. That's one way of helping it. Another way to do it is to control the temperature conditions. But it's, you know, so essentially I'm talking about the thermodynamic limit in the same way that I would tell you that, you know, the thermodynamically most stable state of carbon is graphite. So all diamonds will decay, but you know that that's going to take forever, right? And it's a bit like that, you know. If I've got the biggest grain in my crystal, and then over the other side there's a slightly smaller one, it's going to take an awfully long time for them to achieve that, and effectively it's not going to happen. But there is a tendency for it to happen, and it's worth knowing about that. Generally speaking, that sort of same thing about the cost of surface area will always drive a system to want to have fewer larger things than lots of little things. So we'll see a different case where something else happens about that tomorrow, I expect. Okay, let's just talk about, I just want to talk about the classification of interfaces, if I can. So, what are the kind of distinguishing features of interfaces? They can be sharp, or they could be diffuse. So sharp, what I mean by a sharp interface is that you switch from one to the other over a very small space comparable to the atomic spacing. 1 minute you're in this phase, the next, you know, you move one lattice spacing across or something, you're in the next one. That's sort of the picture that I've been painting, but of course that's not always the case. Sometimes it may be a sort of vaguer, more diffuse change over several atomic distances. And sometimes the width of the interface is an indicator of the relative stability of the two phases. If they're sort of about to switch, for example, from one being more stable than the other, you might start to see a broadening of the interface, because in fact what it means is it doesn't cost you any energy to transform from one to the other once they're roughly balanced, and therefore there's very little energy penalty in having a broad interface over a sharp one. Okay, so you can characterize interfaces by their width as sharp or diffuse. You can also classify them as singular, vicinal, or general. So let's consider FCC. Here is an FCC. The close packed planes in FCC are 1-1-1 planes. Okay. So each of these surface atoms, okay, let's draw the red one, the shade one in red. It has 6 nearest neighbours in the surface plane, does it? In the 1-1-1 plane, which is the top layer here. It has 3 below it to make 9, and it would have 3 above it if it was in perfect crystal to make the 12, but obviously those aren't there. So it has lost, okay, so the red atom has lost 3 nearest neighbours. Okay, so there are 3 broken bonds. Okay, and so that leads to an excess internal energy of 3/2 epsilon compared to the bulk. Okay, if each bond is worth epsilon in energy, okay, then each atom actually is shared between. Each atom has other neighbours down, but typically it's so a bond is shared between 2. That's the point here, right? So you've got 3/2 of epsilon compared with the bulk there. But if I were instead of looking at that, let's look at okay, this would be a 200 type surface. TM1 00 type surface. You can see the face-centered structure there from side on, so it will be the same looking from the top. Now every atom in the surface has got 4 nearest neighbours. Okay, so it's going to cost more. That's going to be a higher energy surface to create. If I go to, whoops. Okay, this would be something like 220, 110, 5 nearest neighbours there. Okay, go on. Go on. Ask it.
Because you have to turn the top into red. Left top you have 3 atoms which are left and 4 bonds which are broken.
Sorry. So
what is missing?
let me just be clear about what I'm drawing here. We could see this as the. Okay.
So the cut is parallel to the board, right?
The cut. No, I was drawing the cut there, but I don't think it makes. I'm just trying to think what difference it makes. I don't think it makes a. In this case, it doesn't make a difference. I think the cut. I think in my intention. This. Yeah. Okay. Let's think about this as the plan, the top view of the interface. So there, if I put a dot, the dot is between the 6 nearest neighbours in the surface plane, and then of course you've just got 3 above it, haven't you, in a triangle, yeah, and 3 below it in a triangle. So you've lost 3 nearest neighbours there. Here, it's this guy. He has 4 nearest neighbours in that plane. He's still got 12 nearest neighbours overall because he's in the close packed thing. Yeah? So he's got 4 there. He's got 4 above, rotated at 45 degrees, and 4 below, rotated at 45 degrees. So he's lost 4. Yeah? The 110 plane is obviously the plane that sort of, we're all familiar with that one, is diagonal. I think I might need to just draw you this out again to answer this question properly. Okay. So this 110 plane is one that is going like this. Okay. Is that okay? So an atom in one of these, okay, if I go and create the surface with that green shaded plane there, like that, yeah, then this atom here, it has 2 nearest neighbours in that plane, which is this one here and the one which is the other side of it here. Okay, so it's got 2 nearest neighbours in the plane. It has 12 nearest neighbours overall. That leaves 10. Half of them would be inside the solid still, and half of them would have been lost. So the 10 divided by half outside, half inside, 5 of them have been lost. You have to go and you have to get a model and actually kind of cut it to work out exactly where they are. But it has lost 5 nearest neighbours. Okay, go on.
Where did you cut the other two examples?
So the other one, this one here, that's just a surface plane. That's just the top face of here.
Okay.
And this one is the plane which is got the normal to the body diagonal, which is the close packed plane in FCC. You familiar with that?
Okay. Yeah.
Yeah?
So the cut is okay.
Yeah? All right. So those are clear. I mean, if I were to give you a crystal structure, you would be readily able to identify those planes. Okay? The ones that have relatively low Miller indices. Yeah? You can do those. But probably, well, you're claiming you can't do those, or I'm sure you can. Okay. Actually, okay. I want you to imagine now, look, let's imagine a simple cubic or something like this now, okay? And I'm trying to create now a surface here, this black line, which makes some angle theta to some key crystallographic direction, which we can easily identify in this crystal, okay? So what we've seen that those low index surfaces have different energies. Okay? So clearly the surface energy per unit area is going to depend upon the choice of interface. Yeah? If I have just 1-1-1 interfaces, then that will be the lowest energy possible. But if I start mixing in some of the others, it will have higher energy. Now let's consider a general case here at some angle theta. Then you can see the dangling bonds, if you like, that this is going to create. All of the squares that are on the outside here, you can imagine there's a dangling bond to a square that ought to be above it, but which is absent now. And also there are some dangling bonds here, additional ones, where some of these squares also are missing a neighbour to the left. So if we now assume that, there's an energy associated with every bond that we must make, and we also say, look, A is going to be the width of one of those squares there, and I consider some length, I'm going to consider some length L along this surface direction, then you can see, can't you, that L times the sine of theta is just the height. In this case it's twice A, isn't it? So actually there are L times the sine of theta divided by A broken bonds which are in this sort of direction, okay, from left to right. And L cosine theta is obviously the length along here. In this case it's 6 times A, but there's L cosine theta over A broken bonds that are pointing in that direction. Is that okay? Now if I allow W, let's call W is the width of interface out of the plane of the screen. In other words, we now assume that this structure now extends out some width W from the screen, then that's another W over A bonds, okay, in this direction. Then we can say that gamma goes like L times W over A squared, so that's the number of broken bonds there, times cosine theta plus the modulus. I'm taking the modulus because, of course, it doesn't matter whether it's at this angle or at this angle. The number of broken bonds is the same, so it's only the modulus of sine theta I care about here. And each of those we've always costed them before at epsilon over 2. Okay, which says that it looks roughly, okay, gamma looks roughly like this. Okay, where this is 0 and this is positive in it. So positive and negative are the same, but if you like, 0 is the lowest possible energy surface because I only have bonds pointing vertically up, don't I? I don't have any left to right bonds. As soon as I start tilting the interface, then actually the number of bonds pointing up doesn't really change much. L has to be a bit longer to accommodate those, so there's a bit more area. Okay, but in addition to those, I start creating the left-right bonds as well, and so away from 0, the energy per surface area increases. So there's a cusp here. Okay, the cusp is reduced a little bit by entropy effects. There's also entropy here, obviously. We're creating some steps here in the surface, and in potentially atoms can now diffuse, and those are quite sort of happy places for a little atom to go and join onto. So there is actually at finite temperature there's some entropy associated with these, but this leads to something that. Whoops. I now draw. Oh gosh. Okay. See whether I can get this right. Okay. So this is called a gamma plot, and it's a polar plot, and I'm plotting theta, okay, against as the angle around. So I don't know, theta is, well, we'll sort that out in a minute. And the distance from the origin is proportional to gamma. So let's suppose that here is gamma 001. So theta at this straight up position corresponds to a 001 surface. Okay. And then let's suppose that this here, I think that's right, these are gamma 111. Okay. Then as I go round, okay, in other words, those low index planes are cusps because they're particularly low energy. And as I start to go slightly away from them, I get this sort of effect going on. Okay? So there are some particularly low energy values that I like to do, that I like to make. And the total surface, the total energy is going to be a sum over all of the surfaces, if you like, of the crystal, I, with the surface energy per unit area for that times I times AI. Yep.
The two inclined lines, are they 45 degrees?
No. No. They're...
What is the variable that brings us?
So it's just orientation. So obviously, in principle, I could have any orientation, but and I can visualize this in 3D. But for the moment, I'd just like you to think that I'm starting with a 001 interface, and now I'm changing the angle of that interface in such a way that at some angle I'm going to come to a 111 termination. Okay, I can choose to do that. And then obviously if I go all the way 180 degrees around again, I will get back to another 001, but it will be underneath. Now I could do that in lots of different ways. So in general this ought to be a 3D plot, but I'm hopeless. You see how hopeless I'm at drawing? There's no way I can draw the 3D one. I'm just trying to draw, just think of this as a picture, okay, general picture. Don't worry too much about whether it's 001 or 111. Just assume that what I'm doing here is I'm starting from a particular surface, which is not the lowest energy surface, and I'm changing the orientation now. So locally it increases like a cusp. And then I keep doing that, but at some point, actually it turns out that I then find an even better interface that is lower energy than the first. That will have another cusp, but it will be closer to the origin because I have lower energy. Yeah.
That's the point of this more basically that the surface will tend to be at the...
Right, so I haven't quite got there yet. I haven't quite got there yet, okay? What the system wants to do to minimise its energy is to minimise this. It wants to choose a set of surfaces I such that the sum of the product of the surface per unit area times the area is the smallest that it can possibly be. Okay, so what will it choose? Well, it will choose this one, and this is where something called the Wolf construction comes on.
Sorry, everyone choose which one?
It will choose the ones that minimise this. Okay, because clearly it can't just be bound by these, because then it's an infinite slab. If it's a finite crystal, it's got to have a selection of them. So which ones is it going to choose? Well, the Wolf construction says you find this by drawing lines from the origin to points on the onto this gamma plot. Okay, and then you start drawing planes perpendicular to this. You imagine doing that for every single thing that you can. Then it turns out that the one thing that minimises, and it has been proved, the thing that minimises this quantity is a construction where you choose the kind of the shape that is inside all of those planes. But because of these cusps, okay, because of these cusps, you can see that that's going to go inside, you know, those points are going to dominate somewhat. Let's try and get this right. That's going to go there. That's going to go there. That's going to go there. And that's going to go there. Okay? And so this would say that the ideal shape of this crystal is one which is dominated by faces which are perpendicular to 111, because they are the lowest energy facets of this crystal. Okay, there is a bit of 001 there. Okay, but actually the amount that you'll get is inversely proportional to the surface energy per unit area for that particular facet. Okay. That's not really within the remit of this course, but as we're passing by, you probably ought to just be aware that thermodynamics is nothing to do with kinetics. Again, kinetics is going to all be to do with the rates at which things can happen, but thermodynamically, the lowest possible energy for a finite crystal is the one that will have this sort of combination of surfaces. And sometimes you can see that. Sometimes, actually, you can do this Wolf construction, and you can look at the sort of shape, the equilibrium shape you'd expect to get out, and then you can spot that actually that's the same as what you see. So sodium chloride. What are the lowest energy surfaces of sodium chloride? See salt crystals? 100, because they're the charge neutral ones, right? It's an ionic crystal, so you can't start creating surfaces that just have chloride ions in them.
right? That would be, right? You're not going to get any of those. You have to have the charge neutral ones. And in fact, the 100 surfaces, sodium chloride, are so much lower in energy than anything else that you end up with cubic crystals. And you can see, right? You can see those. There are other ones where you can see the shape, the form of the crystal reflects the form of this construction. But there are others, if the crystals have formed far away from equilibrium, where this is not relevant, because this is just around thermodynamics. So sometimes it helps you understand what's going on, but not always. Okay?
Just write down what a construction is.
Yes. Wolf. Construction. This was written down by Gibbs. Wolf stated without proof that this was the answer, and then the answer was provided about 50 years later. Okay? All right. So, just to be clear, because I started out by talking about singular versus vicinal versus general, I better explain what those are. So, singular is one that has a cusp, is where there's a cusp. Okay? A single is a singularity, if you like, in the gamma point. A particular orientation that has particularly low energy, right? And you recognise it because it's just a low index surface. Yeah. Vicinal is one that is very close to singular. So a bit like this one here that I've drawn. Okay. Sort of close to 001, but not quite. That would be vicinal. Okay. And that's because, essentially, do you see what the vicinal one is? If you imagine if I took theta down even more, I would just get these steps, and I get broad plateaus of essentially 001 with line defects, these steps in between them, because that's actually the lowest way to organise that surface. So that's typically what a vicinal surface will be characterised by, these plateaus of singular surfaces and then line defects along them, and then general is anything else. All right, and I think that's enough for now.